Testing, testing. Having trouble with the sound, but I've got a great problem for you here. It's a torsion problem with a twist. Let that sink in a little bit. Torsion problem with a twist. So the twist is that it doesn't have two fixed ends, but rather one end has a torsional stiffness to it. So we'll explore that a little bit. We've got this shaft, it's 836 steel, has a diameter of 80 millimeters. It's fixed at NB, and the support at A has a torsional stiffness of K equal to 0.5 meganewton meters per radian, right? So for every radian that twists, right, every 57 degrees that twists, it develops 500 kilonewton meters of torque, 0.5 meganewton meters of torque. If it's subjected to the torque shown, and if we look at it from A, look in at it from A, we first see a 4 kilonewton meter torque that's going this way, and then counterclockwise after that, there's a 2 kilonewton meter. So back here we have 2 kilometer. I think you can see it here. Check on my screen. So yes, this support is a little bit different, but given this information, our goal is to calculate the reactions at A and B. It's still indeterminate. We're going to tackle it the same way we tackle every indeterminate torsional problem. We're going to do the statics, and we're going to develop a compatibility equation. We're going to get the reactions, we're going to get the angle of twist of A, how much A actually does twist, and then the absolute maximum shear stress in that shaft, somewhere between A and B. So to start, we'll do the statics. We got reactions. I've got 4 going this way and 2 going that way. It doesn't matter which way I draw the reactions. Remember, reactions are always your best guess. And if your guess is not great, then you just get a negative value, and it means that it's the same magnitude, but in the other direction. But since I have more going clockwise, I think I need to have counterclockwise reactions at A, the torque at A, and counterclockwise reactions at B, the torque at B. So by some moments about the centroidal axis, right? Centroidal axis. And I look at it, the first thing I see is a counterclockwise to 0. The first thing I see is a counterclockwise torque TA. Then I see a clockwise torque of 4. Then I see a counterclockwise of 2. And another counterclockwise of TB. Those are the 4 torques shown in red acting on this shaft. That equals 0. And if I simplify that, I get TA plus TB equals positive 4 minus 2 equals positive 2. And we'll put the units back in, kilonewton meters, each of those numbers. Indeterminate, I've got 2 unknowns, no more statics equations that will do anything for me on this problem. Sum of forces in the X, Y, and Z don't do anything. Sum of moments about other axes don't produce anything. And so I've got to develop a compatibility equation. And it's going to be the same one. I'm going to leave some space here and come back to this. Let me slide this up. It's going to be the same compatibility equation that we've used in the past, and that is to say the angle of twist of one side, A, with respect to the other side, B, is equal to the individual angles of twist, the angle of twist of A with respect to C, and then C with respect to D, and then D with respect to B. And we've seen how if we go through and we cross out, I got a C in the denominator and numerator, a D in the denominator and numerator. I'm left with A with respect to B, the same thing that I have on the other side of the equation. So the types of problems that we sometimes see is two fixed ends that can't move. We would set this equal to 0. If we had one end that had to rotate some before it engaged, like teeth on a sprocket have to rotate maybe a tenth of a degree before they engage the teeth on the next gear, uh, then we might set it equal to a value. In this case here, the key is the torque is equal to Kv, or angle of twist. This is very similar to spring constant, F equals Ks. The more you deform it, the bigger S becomes. You multiply that times the stiffness, K, the spring stiffness, and the force increases. Greater the S, greater the force, a linear spring. Well, now we have a torsional spring. Maybe you've seen them like this here. And you go to twist it, and the more you twist it, the more it tries to push back. And that's what we have here. How much does it push back? Well, it's specified by this 0.5 meganewton meters per radian. And so with that in mind, the torque at A is equal to K times the angle of twist of A. And that angle of twist is its total angle of twist with respect to some fixed reference. And so we have B on the other side of the assembly that's fixed. So the angle of twist of A is the same thing as the angle of twist of A with respect to B. That's the actual angle that it rotates through. So we have a value for this. We have A with respect to B is equal to the torque at A over K. So let's move on to another sheet and come back to this. We have our statics equation. We have our compatibility equation. I can write one more, right? We always do this. This is TL over GJ of AC. This is TL over GJ of CD. And this is TL over GJ of CB. But in this case, it'll make it a little bit easier if we observe G is the same. G is the same for every section of the shaft. Doesn't change materials. J is going to be the same. It has the same diameter everywhere. And L is the same. Each of these is 600 millimeters long. So I might want to take those out. L over G, J, AC plus taken out the L over GJ, I have the torque in CD, and taking it out, I have the torque in DB. These are the internal torques in the shafts between A and C, between C and D, and between D and B. They're not 2 and they're not 4. It depends on what the reactions. If the reaction is 1 at TB, then all through this section, if I make a cut through it and I look at that end of it, we're going to see that the internal torque is also 1. And then when I come over here, if TB was 1, and then I have another applied 2 in the same direction as TB, and I make an arbitrary cut somewhere between C and D, we're going to see that that internal torque would be the 2 plus the 1, or 3. So we need to know what these are, TA and TB, in order to calculate the internal torques. The way we do that is keep this the same, TB, and we're going to forget about TA for right now, because all we're interested in is calculating the internal torque here, here, and here. And so the first one, I'll draw out a couple of these. They're not going to be pretty. Torque at B. Well, the internal torque, I could draw it either way. There's nothing that's forcing me to draw it. Perhaps positive would be counterclockwise. This is the internal torque in dB. And then I would get that it was equal to a negative TB, equal to a negative value of that. But I'm going to simplify it, and I'm going to go this way and call that the torque in dB. And when I do sum of moments about that centroidal axis, I get internal torque is equal to TB. Right? This, if this is positive, then that's negative, and they become equal to each other when I move the negative to the other side of the equation. Now, the only thing to keep in mind is now that I've picked this direction, I have to stay with it. So when I go to the next one, now I'm out here, and I have this 2 kilonewton meters acting, and I make a cut through it. This is going to be the torque in CD. And so torque in CD is TB plus 2. That's kilonewton meters. And finally, I'll go to the last one. Make a cut in it after the percentage to TB. So this is this cut looking to the right or into the page. This is this cut looking into the page. And this exposes the internal torque in AC. And again, maybe I'll write this one out. Sum of moments about the centroidal axis equals 0. If I go clockwise like that, I have TAC. Going clockwise, I have plus 4. I have minus 2. I have minus TB equals 0. TAC plus 4 equals TB plus 2. That's exactly what it's. That's exactly what I have here, but now I got to subtract 4 off of it. and I'll get TAC equals TB minus 2 kilonewtons. Those are my internal torques. Those are the values that I'm going to put in here, the internal torques. So equals LGJ. TAC is equal to TB minus 2. I'm writing units on one of them so we don't forget it. Plus TCD. TCD is TB plus 2. Plus TDB. TDB is just equal to the reaction at TB. So I'm going to use another page to calculate a couple things and convert everything over into one set of units to make the math a little bit easier as we go through this. All right. So we need those two sheets. I'm going to convert everything into newtons, millimeters. So I'll start with G, 75 gigapascal. That's equal to 75 E3 megapascal. That equals 75 E3 newtons per millimeter squared. So I don't have any meters, I don't have any kilonewtons or meganewtons. I've reduced everything to newtons and millimeters. Let's keep going. Has a diameter of 80 millimeters. It's already in that. Diameter equals 80 millimeters. Radius equals 40 millimeters. All done there. The stiffness, K, equals 0.5 meganewton meters per radian. I'm going to get rid of the mega. And so mega, canceling out in the denominator, means 10 to the 6. And I'm going to get rid of meters. And this 10 to the 3 millimeters per meter, 1,000 millimeters per meter. And so the mega cancels out, the meters cancel out. I'm left with Newton millimeters. And so my equivalent is 0.5 E9, 10 to the 6th, 10 to the 3rd, Newton millimeters per radian. So that's K. So there's the conversions I want to do on this sheet. The calculations I want to do to try and simplify this a little bit is that L over GJ. Let's see what that equals. L over GJ. That equals 600 millimeters over G, which is 75 E3 newtons per millimeter squared. And that's got to be multiplied by J, which is pi over 2, 40 millimeters raised to the 4th. So just looking at the units here, I have millimeters in the top, and in the bottom, I'm going to have newtons per millimeter squared. And when I raise this to the 4th power, I'm going to have millimeters to the 4th. Two of these are going to cancel out with two of these. One of these is going to cancel out with the top, and I'm going to be left with Newton millimeters in the denominator. So you would either say per Newton millimeter, this number is going to be per Newton millimeter, newtons to the -1, millimeters to the -1. I'm going to do this math out now and get a number. 40 raised to the 4th times pi divided by 2 times 75e3 equals, that's my denominator. Looks pretty big, E11. Inverse it times 600 equals, second function scientific, 1.989 E minus 9. L over dj is 1.989 E minus 9 per Newton millimeter. And while I'm at it, and it's easy, I'm going to also calculate the inverse of that. Gj over L is just the inverse of that. That's easy. Hit the inverse key. And I got 5.027 E8. 5.027 E8. And now the Newton millimeters come to the numerator. And so it has units of Newton millimeters. All right, I think I'm ready to go back to the first page and start solving some of this stuff. Here we are. I hope I clicked record. That's good. Looks like I'm recording. It's my left hand on the mouse. I don't want to click the other things. All right. Here's our torsion problem with the twist. Equals L over GJ. Let's put that in. L over GJ is 1.989 E minus 9 per Newton millimeter. And then in the parentheses, we have TB minus 2 plus TB plus 2. That's 2 TB, and the 2's cancel out, plus TB, that's 3 TB. On the other side of the equation, we're going to substitute in TA over K. TA over K. And you're going to see, we have a value for K on the other page. We're going to see that we have an expression that relates TA to TB that will supplement our statics equation. And with the two of them, we'll solve for TA and TB. So I'm going to say TA equals K times all that equals, going back to K, right, 0.5 E9 Newton millimeters per radian. 0.5 Newton millimeters per radian. And I've got 1.989 E minus 9. I skipped something, right? 0.5 E9 Newton millimeters per radian. So we're going to squeeze that in there, E9. 1.989 E minus 9 per Newton millimeter times 3 TB. So I think we all know that E9 times E minus 9, they cancel each other out. You add them together, you get E0, and E times 10 to the 0 is equal to 1. So E9 and E minus 9 cancel out. The Newton millimeters in the numerator cancel out with the Newton millimeters in the denominator. And the radians, remember, radians is a ratio. It's a dimensionless unit. It's not a real dimension. Um, it's a ratio, just like pi is a ratio of circumference to diameter. It doesn't have units. This is a ratio. We put rads in there, but we don't have to worry about that too much. We have TA equals 0.5 of 1.989 is, now we get rid of scientific, is 0.9945 times 3 TB. And when we multiply that times 3, we get 2.984 TB. And now I can substitute that in. TA is equal to 2.984 TB plus TB equals 2 kilonewton meters. Add 1 to this, 3.984 TB equals 2 kilonewtons. And so TB is equal to, take the inverse of that and multiply it times 2, 0.502 TB equals 0.502 kilonewton meters. And now I can substitute that back into this equation or this one. This one looks a lot easier, and solve for TA. So make that negative and add 2, and we get 1.498. TA equals 1.498 kilonewtons. So part A is done. That's the correct answer for the reactions at A and B. Now we got to calculate the angle of twist of A. That's this equation right here. And let's do this. Let's calculate TAC, TCD, and TDV. That's why it has the other sheet of paper. Right. TB is 0.502. And so the internal torque is also 0.502. TCD is TB plus 2, so that's 2.502. And AC is TB minus 2, that's equal to a negative 1.498 kilometers. It's in the other direction, right? But we have a torque going the other direction just before we make that cut, so it makes sense. Those are our 3 internal torques. Probably the easiest. equation to put those into, those that look hidden, is I'll now take this. I think I got room for it down. Bring it down. That says the angle of twist of A with respect to B is equal to L over GJ. That was the 1.989 E minus 9 per Newton millimeter. L over GJ. And TAC is 0.50. TAC is negative 1.498. 2CD is 2.502. Maybe we'll note that the magnitude of the largest internal torque is between C and D. That might help us solve the part C. And that's plus TDB, which is 0.502. And units on the last one, so we don't lose them. So we got to look at these units and make sure we pull that out so it doesn't distract. Right. This needs to be dimensionless. And so one of these units we've got to cancel, got to adjust. We can make this 1498 Newton meters. Kilonewton meters. Get rid of the K, 10 to the third. Get rid of the meters, go to millimeters, 10 to the third millimeters. So I think what we'll do is say this is E6, this is E6, 10 to the third and 10 to the third, and this is E6, and this is now Newton millimeters. I'm just going to cancel out with those two. Mention this. I'm going to do each of these in a separate equation, a separate term, so that we can see how it's twisting. Let me make sure you can see everything. 1.989 E9 negative. And let's store that. Second function scientific, 1.989 E minus 9. And we'll multiply that times 1.498 E6. And that's negative. I think I'm going to leave it in scientific. So the three terms become minus 2.98 E minus 3 radians. That's just for AC, between A and C. And then recall 1 times 2.502 E6, and that's positive 4.98 E minus 3 radians. And recall 1 times 0.502 is E6. Put it 11 again. recall 1.989 times 0.502 E6 equals, there we go. So this says we have to move the decimal 4 places to the left, like 3 zeros and then the 998. So let's make it 0.998 E minus 3. And then rewrite this minus 0.00298 plus 0.00498, right? 3 places over, 3 places over, plus 0.00099. Oh, this should have made a 1 there. Again, all radians. Let's look at these numbers. We've calculated some stuff. We figured out that this is 0.5, it's 0.502. Let's call it 0.5 kilonewton meters, very close to it. And we figured out that this is 1.5, right? We've got 2, doesn't draw on the page. We've got 2 plus 0.5 plus 1.5 is a total of 4 going counterclockwise, and we have 4 going clockwise. This is fixed. B does not rotate at all. This gear rotates, starting at that end, 0.998 E minus 3 radians. So we want to go through and do that. Let's 2 times pi divided by 360 equals times 0.00998. No, I'm trying to do it right. 360 degrees divided by 2 times pi equals, and let's store that, that's the 57 degrees per 1 radian. So if I multiply that times 0.998 E3 negative, I get 0.057 degrees. And if I do 0.0498 times we call 1, I get 0.285 degrees. And 0.00298 times we call 1, I get 0.573 degrees. No. Okay, equal sign. We get 0.171 degrees. So now I'm looking at this here. B doesn't move. That's at 2 kilonewton meters, twisting it that way. D rotates a line that was straight like this, rotates this way to D, and that angle is the 0.057 degrees. any of those three, but 0.057 degrees. Then there's still a positive torque in all this. This rotates how do I want to draw this? Remember, it's not the two that's causing it to rotate. It's the internal torque, which is the 0.5 motion, internal torque. So then the additional, let's say that takes us up to there. And then we get another 0.285. But then the applied torque brings it back down. And this amount right here, see what I can see on the screen, is going to be A with respect to B, which we didn't quite calculate yet. So I'm going to add these together. Let's go, what do I have here? We got the 0.171, which is negative. Add 0.285, add 0.057, and I get 0.171. A with respect to B. Do that again. 0.998 E3 negative plus 4.98 E3 negative minus 2.98 E3 negative equals 2.99. So it's slightly different than the value above. It just doesn't show up in the 0.171. That is part two. And part three is pretty easy. Tau equals TC over J. I don't think we calculated J by itself yet. The largest internal torque is in the middle between C and D. It's 2.502 kilonewton meters. So equals, this is between C and D, 2.502 kilonewton meters. C is the distance to the outside fibers. It's the same as the radius. So that's going to be 40 millimeters. And J is pi over 2, 40 to the fourth millimeters to the fourth. So once again, we're going to do 10 to the 6 Newton millimeters per kilonewton meter. That's going to cancel out the kilonewton and cancel out the meter, leave me with Newton millimeter. It's going to combine with the millimeters in the numerator to be Newton millimeter squared. But I'm dividing by millimeters to the fourth, so I'm going to be left with newtons per millimeter squared, which is our megapascal. Week 1. mechanics and materials, memorized in megapascal is Newton per millimeter squared. So now I do the math. Don't have anything on my calculator. I'll start with 40 raised to the fourth times pi divided by 2. There's my denominator. In the numerator times 2.502 times 40 times 1e6. Conversion factor equals, we get 24.88 or 24.9. Can't erase 24.9. That's all right. I'm going to summarize at the bottom. The reaction at A is 1.498 kilonewton meters. The reaction at B is 0.502 kilonewton meters. The angle of twist with A, which we can leave it as just subscript A, or you can say A with respect to B. It's the absolute amount is equal to 0.171 degrees, and the maximum shear stress occurs in CD, and it's equal to 24.9 megapascals. That's torsion with a twist. It's not that hard. Remember, start the same way, static compatibility equation. Do your substitution. I'm trying to teach you this. You don't need a sheet for this information here. You can look at this and work your way across. You can fit that on this page here. You don't need this sheet necessarily. Might take more than one sheet of paper to do this problem. You could put, right, you know this stuff. You could put all this stuff in the equations here. I was just trying to simplify the equation a little bit and fit it all there. All right. Torsion with a twist, long